In this video, we want to take a look at the definition of a subspace. Even the name itself sort of gives the impression of maybe a vector space inside of a vector space. That's really what it is. Here's the definition. We say that W is a subspace of a vector space V if W is a, first of all, non-empty subset of V, and W is a vector space using the same operations as V. Okay, so before I go into examples that are subspaces, let me say how that last part is very important with an example that's not a subspace. So for instance, if you think of the vector space R1, so just numbers, where, vector addition is just adding numbers and scalar multiplication is just multiplying numbers. We also had that crazy vector space, which was just all the positive numbers, where vector addition was multiplication of numbers and scalar multiplication was exponentiation, right? So certainly the set of all positive numbers is a subset of the set of all numbers. But I would not say that that vector space is a subspace of R1 because it uses a different set of operations. Scalar multiplication and vector addition are different than what standard R1 is. So I need to have a subset, and then I need to use the same vector operations. And if the subset is itself a vector space with those operations, then we have a subspace. So an example here is just let my vector space here be R2, and W, my subset, will be, I don't know if I've used set notation before, but the squiggly bracket means there's a set. This describes what the things look like. So things in this set look like a pair of numbers. So they're elements of R2. And then the bar means such that, and then there's a condition. It's not just any old points get in. W is only the points x, y, such that 3x plus 7y is equal to 0. And in R2, we will use we're in R2, so we use the standard vector addition and scalar multiplication. Now, to see that W is a vector spade, not a vector spade, a vector space, we must check all the 10 axioms, okay? So here we go. Let's see that this in fact works. So let's say we got 2 points, W1, 2 vectors, W1 and W2, that are in this subset W. So the first one looks like x1, y1, and the second one looks like x2, y2. Now I want to look at, right, so the first axiom is closure under addition. So I'm going to look at the sum of W1 and W2 and see if that's in W. Well, W1 plus W2 is this, just add the 2 vectors up. And then there's a question of, if this is what it looks like, is it in W? Now this description right here is it's like a calling card. Actually, this whole set notation thing is like a calling card. Think of W as a very exclusive club, right? And it's Friday night, Friday evening, and people are trying to get into the club. And there's a bouncer at the door, and the bouncer at the door has very clear description as to who can be let in. And first of all, you have to be from R2. So if someone comes up with X, Y, and Z coordinates, he's going to look at them and say, no, you're not a vector in R2, get out of here. Okay. Now, there may be others who come up and say, hey, I have X and Y coordinates and no Z coordinate, right? And then the bouncer will look and say, okay, tell me your X and Y coordinates. And then the bouncer would check. Is 3 times your X coordinate plus 7 times your Y coordinate equal to 0? If so, come on in. If not, you get the heave ho. You're not in, you cannot come into the club. So you can think of this set description here as the calling card, as the conditions that allow you to come into the club W. Okay? So in order to be closed under vector addition, you add the 2 vectors and then you have to see, is this always in W? So if I took 2 things from W and I add them together, do I get another thing in W? Okay. So we got to check. Do we satisfy the conditions to get in W? What's the bouncer at the door going to tell us? So check. 3 times the X coordinate we just got, plus 7 times that Y coordinate. I want to see if that's equal to 0. And, well, distributive property, there's 3x1 plus 3x2, 7y1, 7y2. Move some things around. So the 3x1 plus 7y1 plus 3x2 and 7y2 just... Now, look at 3x1 plus 7y1. I'm claiming that's equal to 0. Likewise, 3x2 plus 7y2 is equal to 0. How do I know that? Well, I know that because W1 and W2 are in the set W. And if they're in the set W, they must have passed. They must have gotten by the bouncer. So they must have satisfied this condition that 3x plus 7y is equal to 0. So x1, y1 satisfy that condition, which means that adds to 0. And then x2, y2 satisfy that condition, and so they add to 0. And then 0 plus 0 is 0. So the sum of W1 and W2, when plugged into 3 times x plus 7 times y, gave us 0. And sure enough, it's in. So addition is closed. Okay. Now, axiom 2. Well, axiom 2 is vector addition commutative? And the answer is, well, of course it's commutative because we already know we're in R2, and that's a vector space, so axiom 2 is true. This has nothing to do with W. Likewise, 3. Is there an associative property? Is W1 plus W2 plus W3 equal to W... I mixed up the order here. It should be W1 plus W2 plus W3. And the answer is yes, because, again, we are in a vector space R2, and we know that it's associative. This had nothing to do with W. I also want to point out here, axiom 4, is the 0 vector in there? Well, yes, I can just double check. 3 times 0 plus t times 0. Goodness, there are so many errors. Here we go. 3 times 0 plus 7 times 0 is 0. So I know that the 0 element from R2 is actually in W as well. So I've got the 0 element in there. Additive inverses. So if I have something in W, I notice that the additive inverse in V would just be, put negatives in front of the x and y coordinates. So, so then I check, is that thing in W? And sure enough, 3 times negative x1 plus 7 times negative y1 is going to be factor the negative sign out. 3 times x1 plus 7 times y1. And if, W1 was in W, which we said it was, then this multiplies or adds up to be 0. And then negative 0 is equal to 0. And so the additive inverse of W1 is also in W. So yes, we have the additive inverses in there. Number 6 is closure of scalar multiplication. So pick any scalar in the real numbers, any number here, and W in W, W1 in the set W. And I want to see is K times W1 in the set W. How do you show something's in the set W? Well, you go walk up to the door and see if the bouncer throws you out, right? What's the bouncer going to check? The bouncer's going to check to see if 3 times your x coordinate plus 3 times your x coordinate plus 7 times your y coordinate, is that equal to 0? So 3 times this x coordinate plus 7 times that y coordinate. The k can be factored out. Then what you have in here is just W1 checking to see if it's in there, and it is, so that's equal to 0. And k times 0 is 0. So k times W1 satisfies the condition. The bouncer lets it go through, and it's in the club. It is closed. The scalar multiplication is closed. 7. This has nothing to do with the definition of W. This is just, is there a distributive property this way? Yes, there is, because you're in a vector space R2, which we already know has that property. Likewise, it has this property. And this distributive property, and then there's this associative property of scalar multiplication that works this way, and that of course is true because that's true in R2. And likewise, is 1 times W1 equal to W1? Yeah, it sure is, because it works in R2, and W is part of R2. So this is a vector space. Now that's pretty tedious to have to calculate all 10 axioms each time, or prove 10 axioms, and really we didn't prove much of them. We had to do some work on, what do we have to do? Number 1, 4, 5, and 6, I think, were the ones we didn't just say, yes, obviously. We had to do a bit of work. So I'm going to have a theorem coming up about what we really need to do to show something's a subspace. Here's another example. This one, in fact, is not a subspace. This description is very much like the last one. 3x plus 7y equals 1. Instead of 0, I'm going to put a 1. Now look at, if I check to see if it's closed under addition, Again, start off the same way as before. Take two things that are in W. That means I know that if I plug the x1, y1 in, I'm going to get 1 out. X2, Y2 in, I'm going to get 1 out because that's now the new description. You know, you come on Saturday night, is a different crowd that's going to be let into the club. And so club W here now has to have 3x plus 7y equal to 1, not 0. Right? And so look at the sum. Well, the sum is still the same as it was before because it's still, you know, vector addition in R2. Add the x components, add the y components. Now let's check. Is this point, this vector, does it satisfy that new condition and get into club W? So W1 and W2 are already in, and we look at the sum. Well, 3 times this x coordinate plus 7 times that x coordinate, distribute the 3, distribute the 7, move some things around. The 3x1 plus 7y1, well, that's equal to 1. And the 3x2 plus 7y2, well, that's equal to 1. And 1 plus 1 is equal to 2, which is not equal to 1. So when W1 plus W2 walks up to the door, the bouncer says, get out. I know that W1 and W2 are in here, but you're not allowed because you add up to 2. And I need people only add up to 1. So this is not a subspace. It is a subset, but it's not a subspace because it doesn't satisfy the 10 axioms. It doesn't even satisfy the first axiom, right? So this is not a subspace. Now, geometrically, they look very much the same. If you think about the graph, the first one was the graph of a line through the origin. This is a graph of a line not through the origin, but still it's parallel to the other one. But not going through the origin means you don't have the zero vector in there either. So you don't have the zero vector, you're not closed under addition. This is just not a subspace. Okay. Now, as I said, it's a bit of a hassle to have to prove all 10 axioms each time. So we've got this lovely theorem that says, if W is a non-empty subset of V, then W is a subspace if axioms 1 and 6 are satisfied. I don't have to prove all 10 axioms. I can just prove 1 and 6, and all the rest follow. Okay. Now, here's my proof. Because V is a vector space, we know that all the axioms must be true in V. In particular, axioms 2, 3, 7, 8, 9, and 10 must be true. Right? They don't have anything to do with W. That's just V. Right? However, axioms 1, 4, 5, and 6 do have something to do with, are certain things in the set, right? Is it closed? Is there a zero? Are there additive inverses? Okay. So what I need to do is I need to show that if I know axioms 1 and 6 are true, then I can also show that 4 and 5 are true. And I already know all the other ones will be true because we're in the vector space V. So here we go. For axiom 4, we know that V, it's given that W is a non-empty subset. So there's got to be something in there. If there's anything in there, which there is, let's pick it. So there's something in W. We're going to assume that axiom 6 is true, right? We'll say if we know 1 and 6, we can get all the others. So if axiom 6 is true, we know that k times W is in W for any k. We know that it's closed under scalar multiplication. So I'm going to say that 0 is in W because the zero vector is 0 times W. Take 0 times any vector, you're going to get the 0 vector. And since we're closed under scalar multiplication, then this 0 times W has got to be in the set, but 0 times W is 0, so the 0 vector is in there. Likewise, for axiom 5, given any vector in W, and again, knowing that axiom 6 is true, we know that kW is in W. In particular, let k be -1. And with k equal to -1, -1 times W is the additive inverse. In R2, that's how you could find the additive inverse, is multiplied by -1. And since that's created by scalar multiplication, we know that this additive inverse of W is in W, and so we have additive inverse as desired. So if I know it's closed under addition, and I know it's closed under scalar multiplication, axioms 4 and 5 follow as well, and all the others follow just because they're the properties of the arithmetic in V, which is the same arithmetic in W. Now, let's take Let's do one more example here of a vector space or subspace. Let's do this V be the set of all vectors. Let V be the vector space of functions, and W be the set of all differentiable functions, so functions that have derivatives. If I take two functions that have derivatives, is the sum of them a function that has a derivative? Well, we know from calculus that the derivative of a sum is the sum of the derivatives. So the derivative of f plus g is a derivative of f plus the derivative of g. Knowing that these two things exist, and we can add functions together, we have that this function f plus g has a derivative, and hence is in the set of differentiable functions. So it's closed under scalar multiplication. No, that would be closed under vector addition. That's addition, right? Now let's do scalar multiplication, axiom 6. Take any function in W and let k be any real number. Take a look at the function k times f of x. Right? This would just be scaling it in the y direction by a factor of k when you look at the graph. Well, do we know how to take the derivative of a constant times a function? Well, yeah, we do. From calculus, we know that it's the constant times the derivative of the function. And since the derivative of the function exists, because f is in W, then we have that the derivative of k times f exists, and we have closure of scalar multiplication. And hence, by the theorem above, this is a subspace of the vector space of all functions. Now, I've seen many times in the past students that they do a little more work than they need to do. It's like they show 1 and 6, and then they go and show Axiom 4 as well. They go, oh, 0's in there. You don't have to show 4 if you've shown 6. 4 is implied by 6 in the point of view of looking at a subspace. Okay. So there you go. There's the notion of subspace. We will do some more with it in the following few videos.